Today, what we're going to do is we're going to revisit the synchronous counter from the last video where we use D flip-flops, and instead we're going to use JK flip-flops. So we keep the state transition diagram the same. That doesn't change. We're still implementing a mod-8 up counter. What does change is the excitation table. So the control inputs are different because now I'm using different flip-flops. I'm using JK flip-flops instead of D flip-flops. So I have 6 control inputs now, and they are J2, K2, J1, K1, and J0 and K0. So 2 control inputs for every flip-flop. Now, what I'm going to do is I want to derive, like I did for the D flip-flop, I want an excitation table for a single JK flip-flop. A little more complicated than the D flip-flop, but that complexity is going to pay off for us later because we're going to have much simpler Boolean expressions. Okay, so first off, how I'm going to derive the excitation table is I'm going to start with a state transition diagram for a single JK flip-flop. So the JK flip-flop has 2 states. The states are given by its outputs Q, and Q can either be 0 or it can be 1. Okay, and furthermore, it can transition at the next clock edge from 0 to another 0. So Q can be 0 again. It can transition from a 1 to another 1, and it can transition between 1 and 0. But these are not unconditional transitions like we've been used to seeing. These are conditional transitions. So it depends on what the values of J and K are. So let's write out the truth table. So for a JK flip-flop, the hold condition, I have the reset condition, I have the set condition, and I have a toggle condition. Then is in this state here, 0. And I'm going to look at this transition over here. If the Q output is 0, what is going to cause the Q output? What values of J and K do I need such that at the next clock transition, Q remains 0. It stays 0. So that can happen when if I'm in the hold condition, if J and K are both 0. So let's write that here. So J equal to 0, K equal to 0. And it can also happen if I'm in the reset condition. So if J is 0 and K is 1. So let's write that down. J equals 0, K equals 1. And you can see now it actually doesn't matter what K is. K can be 0 or 1, but as long as J is low, I will transition at the next clock edge back to a 0. Okay, let's do the same, but looking here over at 1. So I'm looking at this transition here. So I said it's not unconditional. It depends on what the values of J and K are. I'm going to write them down. So if I have a 1 at the Q output, and at my next clock edge, I also have a 1. Well, that can be because I'm in the hold condition again, right? So my next Q is the same as my present Q. So let's write that down. So I could be in the hold condition. Or I could be in the set condition over here where J is 1 and K is 0. Now it doesn't matter what j is, because regardless of whether j is 0 or 1, if k is 0, the next transition is still going to be a 1. Q is still going to be a 1. Okay, what about the transitions here from 0 to 1 and 1 to 0? So let's look again at the transition from 0 to 1. So if I have a 0 and or at the Q output, and at the next clock transition I have a 1, well, that could be for two reasons. It could be either because I'm in the set condition, or I'm in the toggle condition. So a 0 becomes a 1 in the toggle condition. So let's write that down. It could be in the set condition where j is equal to 1 and k is equal to 0, or could be in the toggle condition where j is equal to 1 and k is equal to 1. And now I see that for this transition, it doesn't matter what the value of k is. K could be 0 or 1, but as long as j is 1, I will transition from a 0 to 1 at the next clock edge. Okay, and now let's look at this transition here from 1 to 0. So I can transition from 1 to 0 at the next clock edge if I am in the reset condition. That's this over here. So I'm going to write that. So the reset condition is j is 0 and k is 1. And the other way that I can transition from 1 to 0 is if I'm in the toggle condition and j is 1 and k is 1. You see that for this transition, it doesn't matter what the value of j is. As long as k is high, the Q output will transition from 1 to 0 at the next clock edge. And now we can go write our excitation table. In an excitation table, I have a present state, Q, a next state, Q plus, and I'm going to show the control inputs. The transition from the present state to the next state. So I have 4 rows in this truth table. I can have a 0 and remain 0. So that corresponds to this transition here. I can have a 0 and the next state will be a 1. I can have a 1, next state will be a 0. I can have a 1 and the next state will remain a 1. And what do the control inputs need to be? So let's look at our state transition diagram. So we can always read an excitation table from a state transition diagram. So let's look. So over here in this row, we said already that corresponds to this transition where I have a 0 and in the next state I also have a 0. So I said that actually it doesn't matter what k is as long as j is 0. So I'm going to write here j is 0 and k is, I don't care, it doesn't matter. Okay, what about this row over here? So if that's a 0 to 1 transition, that's this over here. And we already determined that actually, as long as j is 1, it doesn't matter what k is. So let's write that. J is 1. K, it doesn't matter. K can be 0 or 1, but as long as j is 1, that transition will occur. Now, what about over here? That's this transition from a 1 to a 0. And here, we said that k has to be high. We don't care what j is. So as long as k is 1, j can be anything. And finally, looking at this transition over here, that's this. And we said that for this transition, it doesn't matter what j is, k just has to be 0. What j is. So j is x and k is 0. Remember, this excitation table is there is this kind of mirror symmetry that's happening along the diagonal here. So I have 0x, 1x, then I have x1, x0. So it's certainly easier to remember that than it is to derive the entire state transition diagram. But of course, if you know how to do that, if you know how to do this, then if you're stuck on a test or something, you can always resort to that. To my excitation table now. I'm going to do the same, I'm going to follow the same methodology that I did for the D flip-flop. So I'm going to start one flip-flop at a time. So I'm going to do Q2, present state, next state, and then I'm going to look at what the control inputs have to be to move me from the present state to the next state. And in this case, in the first row, I'm going from a 0 to a 0, and that corresponds to this row of the truth table. So I'm going to write J2 and K2 are 0, X. And over here, I'm going from 0 to 0 again, so that's another 0x. And I have another 0x over here. But in this row, I am moving from a 0 to a 1, and that's this row of the single JK excitation table. So I'll write out 1x. And now I have a 1 to 1 transition, and that's this row of the truth table. So, or I keep saying truth table, but it's an excitation table to be more precise. X0. And over here, I again have 1, 1, again have 1, 1. So that's going to be X0 for the next two rows. And here, 1, 0, that's this row. So I'm going to write X1. And now I'm done the flip-flop corresponding to Q2. So what about the flip-flop corresponding to Q1? So again, I am going to look at this row corresponding to Q1, next state Q1, and I am filling in these control inputs here, J1 and K1. So if in the first row here, I'm transitioning from a 0 to a 0, so I already know that's a 0x. Transitioning from a 0 to a 1, that's a 1x. I'm transitioning from a 1 to a 1, x0. I am going from a 1 back to a 0, so I need to write x1. And over here, 0 to 0, that's a 0x. Here, 0 to 1, that's 1x. A 1 to 1, x0. You're getting the hang of it, I'm sure, by now. So I'm just going to move a little bit more quickly. We've got an x1 over here. And now for J1 and K1, J0 and K0, I am looking at present state Q0 and next state Q0. So 0, 1, 0, 1, 1x. Now I have a 1, 0, so that's x1. I have a 0, 1 again, which gives me a 1x. I have a 1, 0, which gives me x1. And I'm going to just fill them all out in the same way. There we go. And now I need to derive 6 Boolean expressions now. So one for each of the control inputs. So I'll start with J2 and K2. So again, I'm expressing each of my control inputs in terms of the present state. K-map down. And now I'll do the K-map for J2. But I'm going to need all of these. So So I'll just write them out now. So let's fill out J2. I have 0, 0, 0, 1, and then X, 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 X. So just simplify like that. And what do I get? I get J2 is equal to, I wrote my K-map wrong. And now that I have the correct K-map, I can see that it is equal to Q1, Q0. So these expressions, I have more of them. I have 6 of them corresponding to 6 control inputs, 2 per flip-flop, but they are simpler because I have a lot of don't care conditions. So let's look at K2. I'm reading off this column. So I've got X, 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 0, 0, 0, 1. And actually, you're going to see that, in fact, it is the same. So I have the same Boolean expression that I had for J2. So J2 and K2 are identical. Now, what about J1 and K1? J1, I'm looking at this column over here. So 0, 1, X, X, 0, 1, X, X, and that J1 is just equal to Q0. K1 now. I am looking at this column, and I've got X, X, 0, 1, X, X, 0, 1. And in fact, hey, look at that. It's the same as J1. So equal to Q0. And I actually don't need to do the K-maps for J0 and K0 because looking at them, I can see that with all the don't care conditions, I can just say that J0 and K0 are both high. And there is, in fact, a kind of symmetry to this. So as you expand to have more bits, so again, for this would apply to natural mod counters, 2 to the n counters, using JK flip-flops. There is actually a, I guess, a generalization. So I can extrapolate to higher and higher number of bits. So in general, the least significant flip-flop, as we can see here, so that would be the control inputs J0 and K0. So those are wired in toggle mode. J1 and K1 is equal to Q0. J2 and K2 are equal to the ANDed Q outputs of the 2 previous stages. And if I had a J3 and K3, so if I was doing a mod 16 up counter, then I would have J3 and K3 equal to Q2, Q1, Q0. So the ANDed Q outputs of all the previous stages. So we'll draw out the schematic to build this schematic. So let's take our Boolean expressions over here and we'll move them over to a new page. Boolean expressions, and now we're going to do our schematic. So work roughly the same way that it did for D flip-flops. So I'm going to put, I need 3 flip-flops, and they're JK type. I don't really care what kind of edge triggering I have. So This is a distinction from ripple counters. In ripple counters, I cared, but now it doesn't matter. I just want there to be a transition at the clock edge. And again, I'm going to wire up the same common clock to all flip-flops. And I have not shown them, but S bar is equal to R bar is equal to 1. These are sometimes called pre and clear, but they're almost always active low, and we want them inactive, so we're wiring them high. And again, I'm going to put J2 here, K2. So I'm going to go from most to least significant bit left to right. Here's Q0. Okay. We don't really need the bars, but I'll put them anyway. All right, so here I see, let's start with the least significant flip-flop first. So I see that actually J0 and K0 are just wired high. And actually that makes sense because the least significant flip-flop is toggling at every clock pulse. So these guys just wired high. Now, J1 and K1 over here, J1 and K1 are just wired to Q0. J2 and K2 are also the same, so they're wired together, and they're wired to the ANDed output of Q1 and Q0. So here we go. And that's the schematic for our mod-8 up counter using JK flip-flops. This makes a kind of logic. So these Boolean expressions for the control inputs do make a kind of logic here. So let's go take a look at the count sequence, and we can see that in fact Q0 is toggling at every clock edge, and Q1 is toggling at the clock edge only when Q0 is high. So that's how we get this Boolean expression for J1, K1 in toggle mode only when Q0 is high. And over here for Q2, we can see that actually it's only going to toggle twice in this in our state transition diagram, once over here and once over here. And that occurs when both Q1 and Q0 are high. And when that happens, at the next clock edge, Q2 will toggle. And again over here, Q1 and Q0 are both high. And at the next clock edge, Q2 will toggle.